Hello, Jimmy Teague here, shift training instructor for Bloomington City Fire Department and also a college instructor for Ivy Tech State College. Today's video, I want to touch on the principles of friction loss. A lot of people seem to have issues with friction loss, so I want to show you two methods that I use in order to help you actually figure out how to do the equations, because really, if you follow these two methods, it's pretty simple on how to do the equations. Now, first off, what's friction loss? Now, friction loss, the importance of friction loss, understanding it, is whenever we buy fire nozzles, whether you're using smooth bore or a combination nozzles, they're all designed to be able to flow a certain amount of gallons per minute at a certain PSI. Now, when you take in considerations fire hose, especially if it comes from different manufacturers, they all vary a little bit on the inside diameter, and the water that's rubbing against the inside of it actually will affect your pressure. So if a nozzle is rated to flow 185 gallons per minute at 100 psi, because of the friction loss, you're not going to get 100 at that nozzle if you just set your pump at 100, because of the length of the hose, the diameter of the hose. If it has sharp bends, kinks, if you put appliances such as gated valves, manifolds, all those will actually affect your friction loss. Now, there is different types of equations on figuring out friction loss. One of them is what we're doing today is fire hydraulics is different than field hydraulics. Field hydraulics is when you use in the field, like the condensed Q method or using the hand method, where in the field you're not going to pull out a calculator, even though that is an option. They do have hydraulic calculators. You can punch in the length of the hose, the diameter, the gallons per minute, and they'll tell you the friction loss. Or there's also flow charts you can use as well. But for this purpose that I'm showing you here, this is used for when you're sitting around at the breakfast table with the guys. If you're a new driver, you're trying to figure out what your pressures need to be set for each nozzles, for each cross lay, pre-connects, or say you got a yard lay in the back. This is a way of being able to figure out what your pressures should be. It's the ballpark, because this is kind of a theory. It gets you close because every hose diameter changes the factor. Now, if you want to get more specific and to actually get it, best way to doing this is using flow meters. But not all departments have flow meters. Not all fire trucks have flow meters on the actual gauges themselves. So that's another method of doing it. The main reason for doing this is, say you're speccing out a truck and you're buying a different manufacturer hose, which I don't recommend. I'd recommend sticking with the same brand, so that way your friction loss is going to be same across the board, hopefully. But let's say you're speccing on a truck and you're thinking about adding a task force tip. Say it flows 185 gallons per minute, for example. I'm just using that because that's what some of our nozzles are rated at. If you do the equations and you figure out that, well, you know what, if I put more than 200 feet of hose on that, if I'm using, say, 1 3/4 inches, anything beyond that, I'm pushing the maximum capacity of what that hose can handle on pressure. Because if you look at your hoses, they'll have a pressure rating that is set on it for what they're tested at. And you want to make sure you're not going to push it close to that, because the hoses could fail. So where I'm going with this is, whenever you're speccing a truck out, and say you were speccing out a 185 gallon per minute nozzle, you're putting 400 feet of hose on it, and you're thinking, hey, well, why not throw another 200? Do the equations, you figure out you're pushing the limits, you're exceeding that. So what you could do is one of two things: either increase the diameter of the hose or drop the gallons per minute down. So this is the reason why the equations are pretty beneficial in helping you spec out a truck. So for class purposes, let me show you my two methods. So method one is, if you look on my board, I've already written out friction loss equals CQ square L. And C is always going to be your coefficients. Now over here on the board, I wrote out my coefficients, which 1.5 inches is 24, 1 3/4 inches is 15.5. Now let me stop here. 1 1/4 is 1 3/4 inch hose with 1.5 inch diameter couplings. So your 1.5 inch and your 1 3/4 inches, you could actually connect the two together. Don't do it, but they're the same fittings. When you look at the math though, when you're figuring out friction loss, this is your loss. 24 is a significant larger number than 15.5. We're talking 1/4 of an inch. So a lot of people no longer use 1.5 inches. We pretty much use 1 3/4. I use 2.5. Coefficient's 2, 5 inch. This is my department. Some departments use 3-inch hose, so you'll probably want to throw this in. But a lot of your equations, these are the numbers we're going to use, and for today's example, that's what I'm going to use. Q square L, the remaining portion of the equation. Q, this is where people mess up on doing the equations. Q means gallons per minute, quantity, if you will. Quantity is per 100 gallons. Length of hose is 100 feet. So this is my first method on actually doing the equation, is to break it down or write it out exactly how you're going to do it. So let me do this in, let's do purple. So how you really want to write this equation down in order to be able to answer it correctly is write down C times, I'm going to write it out, gallons per minute over 100, and you're going to square it, and you're going to times it by the length of your hose, by 100. That's exactly how you're going to punch these numbers in. So let's draw this out. I'll do this in green. This is my second method. Draw a picture. Now this is a simple, easy equation, so you can probably remember a lot of this stuff, but when we get into more complex ones, it's going to be a little bit trickier to remember all this. So I said this is what, 1 3/4 hose. So I'm writing this down on my picture. Overall, if I remember right, I said 200 feet, which would be 4 sections if they're 50-foot sections. My nozzle, what did I say, 125 gallons per minute? Okay, so let me do this in purple. So 1 3/4 inch hose, that's important because I need to know my coefficient, which is 15.5. And I am timesing that by my gallons per minute, which is 125. Remember, that's over 100. That's going to be squared times, and it's 200 feet of hose over 100. So if we break this down even more before we even punch it in, this would be 1.25 squared times 2, because the zeros cross out. And you punch that in your calculator as it sits. And you're going to get something along the lines of 48. Now you'll get 48.4375, but you know, we can't punch that in on the thing. So you get 48 PSI that you're losing. So if you're using a combination and it's you need 100 at the tip, you're losing 48. So you got to add that 48. So you're going to flow 148. Now, if it's 75, you got a low pressure setting. Well, you just add 75 to that. So 48 plus 75, you're going to set you're going to have to set that at 123. So you can see where you can actually save quite a bit. 148 versus 123. I mean, that's significant. So that means we could actually add more hose if we needed to extend it. So let's do a more complicated problem. Okay, so let's do a little bit more complicated problem. Let's say we have a fire truck, and again, make sure you write this out exactly like how you're going to plug your numbers in. And I mean, as silly as it sounds, you know, draw a picture of your fire truck, you know. Let's say you're running 2.5 inch hose off to a gated Y to the equal same. I said this was 2.5 inch hose. Now let's say it's, I don't know, 200 feet. And then off of this, we're running, I don't know, let's say we did 200 feet off each one of these. And the size of this hose is 1 3/4 inches. And let's say we're flowing, let's say 110 gallons per minute off of each one of those. Whoops. 110 off each one of those. Okay, so if we start from over here on this side, so my friction loss for my 1 3/4, whoops, this is going to look something like, if I'm looking at my coefficient here, it's 15.5. Since these are the same, the pressures are going to be the same, so we only have to do one equation. Now if this was 100 feet longer, we would have to go with the longer one. But your pressures are going to be the same. So my gallons per minute, we know, is 110. You remember that's over 100 gallons per minute for the equation, which is going to be squared, times the length of my feet of hose is 200, which is over 100 feet. So if we break this down further, it's 15.5, which is times 1.1 squared times 2. My friction loss is going to be my friction loss is going to be 15.5 times 1.1 squared times 2. My friction loss is going to be 37.5. So let's make that 38. Now we figure out where our friction loss is from here to here. The friction loss from this point to here and from here to here is going to be the same. It's going to be 38. So we only have to do the equation once. We don't add 38 plus 38 to get, you know, what is that, 76? It's only going to be 38. Doesn't matter which direction, as long as they're the same diameter, same length, same gallons per minute. We're going to lose 38 from here to here. It doesn't matter if it goes this way or this way. So going back to here, 2.5. So dealing with 2.5, the friction loss for 2.5 is going to be, coefficients changes, it's going to be 2 times my gallons per minute. Here's the tricky part. This is where you add the two lines together. Because if I'm flowing 110 gallons here and 110 gallons here, we know we're flowing 220 through the 2.5 to get 110 out of each one. So that's what, 240? Or I'm sorry, 220. 110 plus 110 is 220. That's over 100, which is going to be squared, times your length, which is 200 feet. If we break it down further, that's 2 times 2.2 squared times, because these cross out, 2. So punch that in your calculator and you should get something like 19.36. Now rule of thumb, if this is over 5, we round up. But so 19 plus 38 is 57. So in order to make this work, if these are combination nozzles that flow 100 gallons per minute, or I'm sorry, 110 gallons per minute at 100 psi, because we're losing 19 psi here and 38 here, adding those two together, you get a total of 57. So my total friction loss is 57. If I need 100 here, you're going to 7. Since I intend on this being a short video, what you want to take in consideration is your appliances. Now, if you're looking at your textbook, you need to take in consideration your appliances. If you're flowing more than 350 gallons per minute, that is a quiz question, I guarantee you. Master Streams is 350. Same thing with your appliances, such as your Ys, Siamese, gated valves, any of that. If you're flowing more than 350, you'll have to add 10 psi to this. We're flowing 220, that's below 350, so the pressure below 350 gallons per minute, friction loss is so insignificant that we don't count that. Now if we want to change these out to master streams, which they say regardless of flow, that never changes. I believe it's what, 25 psi per appliance. Then you're going to add in your appliances. If you take your nozzles and say these are running uphill, you know, you're going to add in your elevation pressure gain. If you're going downhill, you're going to subtract that number off. Now so far, we're keeping it simple because we're talking about combination nozzles. If you want to know if it's a combination nozzle versus a smooth bore, if it gives you the gallons per minute, it's a combination nozzle. If they give you the measurement, it's a smooth bore. So let me show you how that changes. Okay, so let's go ahead and keep this equation we had up. The last equation, if you remember, I had combination nozzles are flowing 110 on each line, which requires 100 psi at the tip. Our friction loss overall was 57, so we got set at 157. Let's see what happens when we switch these over to smoothbore tips. So I'm just doing it randomly. Let's figure I'm going to install, make these 3/4 inch. These are 3/4 inch tips. Now, in order to be able to do this equation, we've got to be able to figure out how many gallons per minute that is. So going to this formula up here, gallons per minute equals 29.7 times diameter squared times the square root of nozzle pressure. What this would look like is, if I can write over here, GPM for ½ inch would be 29.7 times diameter squared would be 0.75 squared times the square root of 50. Now when we do this equation, if the number becomes higher than 350 gallons, we're going to have to stop, redo the equation, because if it's over 350, we're doing a master stream. So we need to stop and redo it. But for this purpose, let's see what that comes out to. So I'm just going to put it in the calculator like it says. I get 118 gallons per minute. That's for each line. So now we can go ahead and figure out what our friction loss is on this 1 3/4. So 1 3/4, the coefficient is 15.5. So 15.5 times your gallons per minute, which is 118, over 100. We're going to square that times your 200 foot over 100. This comes 15.5, 1.18 squared times 2. So what does that look like for your friction loss? Well, let me tell you. So we'll punch that in our calculator. So I got friction loss of 43. It's 43.16. So now how much water's flowing through this 2.5? Well, we're supplying 2 1 3/4. So we've got to add these together. So that's what? 236. Punch in the calculator, make sure that's right. 118. 236. So I'm flowing 236 gallons per minute. So my friction loss, let's see, my coefficient for 2.5 is 2. I am flowing 236 gallons. And as you do this, you'll realize you probably won't even write this out. You'll just do 2.236 squared times your length of 200 foot. So 2 times 2.36 squared times 2. My friction loss now for just the 2.5, 22.27. So we can just stick with the 22. So our friction loss for the 3/4 at 200 feet is 43. Our friction loss for the 2.5 is 22. We add those together. That is what, 65? Let me use black. So that's, yep, 65 plus our nozzle pressure is 50. What's that, 115? So here's the scenario where we had combination nozzles are flowing 110 gallons. We're flowing 220 roughly, but let's just keep it simple, 110 per line. And we had to set our pump to 157. Now, some people's SLGs years ago, our pressure relief valve was supposed to be set at 150, so 157 is not doable. You had to, of course, crank it up. Now, if we use smoothbore tips, we can set it at 115. That's a huge difference from going to a smoothbore, going from a combination nozzle to a smoothbore. And the thing is I'm just showing you, I'm flowing 110, I'm flowing 8 more gallons and roughly 42 psi less pressure that I need. So I could actually add more hose to extend that. So, but this is just kind of giving you a way of, like, if you were setting up your truck, that just changing the nozzles, I'm still flowing the same. Actually, I'm flowing more water by using smooth bores. That gives me more friction loss to be able to play with. Now, hopefully this gives you a little bit better understanding. Now, like I said, my 2 methods is real simple. Make sure you write it all the way out. This is gallons per minute per 100, so you're always going to divide by 100 to get that number. Your length, you're going to divide by 100. And then when you get into some of the more complex problems, it's hard to remember everything that you got to go through. You don't want to keep going through the equations and looking at the numbers plus the words. Draw the picture out, because this way it's going to give you a better chance of actually figuring out the equations. Now, one other little thing I want to throw in that sometimes seems complicated, but it's really not, is they'll ask you what your net pump discharge pressure is, like NPPDP equation. And pretty much what it is you need to figure out what your appliance or your nozzle pressure. Using this example, smooth bore is 50, our friction loss was 65, so we need 115 psi to get here. So what's net pump discharge pressure? That is what the pump has to actually add to the incoming pressure to get your 115. So let me show you with a hydrant. Let's say we go ahead and we hook up a hydrant. And off this hydrant, like I said, it's always best to draw a picture. We're getting, I don't know, let's just say we got a decent pressure and we're getting 90 psi off of this. Well, real simple, 115, which is what we need. We're getting 90. So this would be what? 25? So if we have 90 coming in, my truck only needs to produce 25 psi. I get to just throttle it up just a little bit. So as you start driving trucks and pumping, you'll realize that if you got good supply source coming in, good pressure, your truck won't be running or working as high. The RPMs won't be up as high. It's because it doesn't need to do that much work to be able to get you those higher pressures. That's the reason why pump capacities are based on worst case conditions, which is drafting. So to get those PSIs that you need, that engine's going to be running a lot harder than it would if you're hooked up to a hydrant. So one other thought to think about, it's kind of old school, you don't see much, but two-stage pumps, for example. Years ago, people tried to explain to me a two-stage pump, and they always give me the misinformation. So what you got to think about is two impellers, two pumps that are on the same shaft, they're spinning at the same RPMs, creating the same amount of pressure. Now, a two-stage pump, what it'll do is it'll do one of two things. It'll either split the water in half, and the water goes to each impeller, then comes back together and goes out, which is known as running parallel or volume. What that does is, say you're flowing, I don't know, let's use the equation here. That's flowing what? 236 gallons per minute. That means only 118 gallons is going to each impeller, and then when it comes back together, it's flowing 236. With it in that mode, if you weren't being supplied with a hydrant, it has to supply the full amount of pressure, which is the 115. Now, series, that means you gotta remember those two impellers are running on the same shaft, they're going the same RPMs. The difference is that transfer switch has the water go from one impeller to the next impeller, then out. So in series, what you're doing is you're flowing the full 118 gallons per minute. Actually be the full 236 is what we'd be flowing through here. It's going from one impeller to the other. The difference is we need 115 psi. It's splitting the psi in half. You get 57.5. So in theory, with the impeller, when that water hits that first impeller, it's spinning or churning that water into velocity into pressure at 57.5. So it's coming out at 57.5, assuming that's coming zero. Technically that wouldn't be true, but go 57.5. When it hits the next one, it's going to hit 57.5 to give you a total of 118 psi. So the water in series or pressure, it doesn't have to work. It doesn't have as many RPMs as it does in volume. So hopefully that gives you a little bit more insight when it comes to fire equations and a little bit of actually understanding fire trucks. So hopefully this gives you a little bit of guidance and a little bit of help. But if not, feel free to reach out to your local on-shift fire instructor or guys that are really good at this, or rewatch this video. Like I said, the main two methods to doing this equation is making sure you write it out exactly how you're supposed to. Break it down, draw a picture so you can see everything and make sure everything's accounted for so you don't overlook something that's in the equation. So I hope this helps, and take care.